when we left it was winter, and now it is spring. And isn't that nice? There's hope. All right, these are the reactions that we are going to be looking at. This is the first set. We talked about this one in Chapter 7, addition of halogen acids. We're going to do HBr peroxides today, addition of halogen, addition of hypohalite, hydration, and this is hydration, a little bit more civilized. We're also going to do hydroboration oxidation, simple reduction. This is conversion with either osmium tetroxide or permanganate to get 1,2-diols. We're going to make cyclopropanes using carbene addition. And then finally, in our oxidations, we will make epoxides. We will split our double bond with either ozone or with permanganate. Now again, it looks like there's a lot here, and there really is, to be honest, but we'll try to approach these things in a very systematic way to make it easy to understand and remember what's happening. All right, Chapter 7, we looked at this guy. The kinds of things that you need to learn to say to yourself when you see an organic reaction, or things like this. We have an alkene, so you simply identify the functional group. We're adding HBr. What you should say is, okay, addition of HBr. We're going to form an organohalide, organobromide in this case, and the bromine is going to be attached to the carbon that would form the most stable carbocation. Those are the words that you need to remember. Carbocation in this case would look like this. It's on the secondary carbon. Carbocation here would be primary, that is unstable. We know that this is Markovnikov's law. Remember that when you think about Markovnikov addition, don't waste your time counting hydrogens and stuff like that. What you want to do is simply look at the carbons involved and ask the question, which one is going to give the most stable carbocation? Once we have the carbocation, the next step is simply addition of bromide anion to the carbocation. It can come in from either the top or the bottom, because it's flat, and we get the alkyl bromide. So this is the kind of understanding that you need. You need to be able to look at a molecule and say, or look at a reaction that we given this part, and just say, okay, HBr, carbocation, add bromide to the most stable carbocation, etc. Now, this is the ionic addition of HBr. If we do this reaction in the presence of not just HBr, because in this particular case, we're going to get the carbocation here. Again, we would add to that point. But if we take and we dump in peroxides, peroxides totally change what happens in terms of our product. Instead of the 2-bromo alkane, in this case, we get the 1-bromo. Now, what peroxides do in a reaction like this is that they split. This is a generic organic peroxide. Hydrogen peroxide, both of these R's would be hydrogens, right? Well, peroxide, the oxygen-oxygen bond can easily split homolytically, and what you do is you wind up with peroxide radicals. So this is a radical addition reaction. We split our peroxides and we make our radicals. In order to form the alkyl bromide, this radical must then react with HBr, And what it's going to do is simply abstract a hydrogen atom from HBr, and it's going to leave the bromine radical. The bromine radical is the thing that's going to add to the alkene. Now think about radicals. We're going to do a whole chapter on radical additions, but in a radical, we have a single unpaired electron. Things like to be paired up, don't they? Radicals in general are very, very reactive substances. So once we form this bromine radical, it's going to be looking for a source of electrons. Source of electrons, of course, is going to be our carbon-carbon double bond. What happens is the bromine radical will approach the pi system here. It will remove an electron from the pi system, form a bond, and we will leave a carbon radical behind. Process looks like this, and this is our radical intermediate. Now, note what happened here. We added the bromine to our terminal carbon here, right? And that gave us a secondary radical. If we had added the bromine to the secondary carbon here, we would wind up with a primary radical. Carbocation stability and radical stability parallel each other. So everything that you already know about carbocations, you also know about radicals. Instead of adding to form the most stable carbocation, all you're doing is adding to form the most stable radical. Now that makes sense, doesn't it? Once we get the carbon radical, it's even more reactive than the bromine radical was. It will react with another mole of HBr, yank the hydrogen atom off, stick it on, and what are we left with? The bromine radical again. This then undergoes a chain reaction until we get termination of some sort. So we start this reaction with a peroxide of some sort. Peroxide generates bromine radicals. They add to form the most stable radical. That then pulls a hydrogen off of HBr, gives us our product, and bromine radical. This product is described as anti-Markovnikov. That's a real term because the bromine, if we did the ionic addition, it would be bonded to this carbon, wouldn't it? Anti-Markovnikov, we get just the opposite regiochemistry. Any questions? Yeah?
So bromine is the primary radical?
Bromine is just a bromine radical. Just a bromine atom missing one electron.
What's the primary radical?
Primary radical, here, this is a radical on a secondary carbon.
Oh.
If we had the radical up here, it would be a primary radical. Let's look at a couple radicals. This is the methyl radical. This is what's called a calculated spin density. The lone electron has the property of spin, and you can calculate where this electron resides in a given molecule. Radicals are essentially sp squared, not quite, but essentially. And for the methyl radical here, if you calculate where the electron is, it kind of looks like it's in this sort of p orbital sort of thing, above and below and whatever. Fairly localized here on the carbon. This is a tert-butyl radical. We did the same calculation. Here is our p orbital. But the thing that you ought to notice that's kind of neat, first of all, it's actually not quite clear. We'll talk about that in chapter 10. But also note that the spin density doesn't just live on the carbon, but it also lives on all these attached groups. That means that the electron, if you will, spends some of its time away from the carbon and out here. Remember, our fundamental rule is if we spread out a charge, if we spread out, in this case, radical character, that makes it more stable. So the tertiary radical, much more stable than a methyl would be. And the order is exactly the same. We do resonance stabilized as the most stable, tertiary, secondary, primary, and then methyl. Any questions? All right, well, let's do a couple then. What you want to do is look at your reactions. Just like we said with the ionic addition. You look at this and say, okay, it's an alkene. I have HBr and peroxide. I know this is going to be a radical reaction. I'm going to form the anti-Markovnikov product. That means that the bromine will be added adjacent to the carbon that would give the most stable carbocation because it wants to form the most stable radical. Now, sometimes on exams, I make some of these problems two-step, where I ask you to first of all draw the most stable radical. For this one, the most stable radical is going to be at this carbon here, the tertiary carbon. The most stable radical would look like this. Bromine radical is added to the terminal carbon to give us the tertiary radical as our first intermediate. This is then going to pick up a hydrogen from HBr and give us our final product. Again, if you look at this, you would say this is anti-Markovnikov. Because in the ionic addition, you would want the bromine as a tertiary carbon. Here it's on the primary carbon. Go ahead and do the most stable radical for the next one. Here we have a chlorine. Remember, a chlorine has 3 pairs of electrons around it. That means we can do resonance, can't we? The most stable radical is therefore going to be at the carbon bearing the chlorine. So bromine will add to the other, and this is our most stable radical. Once we have the most stable radical, this simply abstracts a hydrogen from HBr, and we get our 1,2 dihalide. Here we have propene. Simply adding HBr peroxide, we have a choice of a primary radical or a secondary radical. Secondary radical will be more stable. Therefore, bromine adds out here to the primary carbon. This picks up a hydrogen, and we have 1-bromopropane. Our last one here. This is benzene ring. What is this carbon here? It's what we lovingly refer to as a benzyl carbon, right? Carbon adjacent to our benzene ring. We know that this is a very, very stable carbocation, isn't it? Well, it's also going to be a very, very stable radical. Therefore, our most stable radical is going to be here at the benzylic carbon, That means bromine adds out here. And once we have our stable radical, this will then abstract hydrogen from HBr, and there's our product. So when you see halogen acid, thing that you look for is whether it's just a simple ionic addition or whether it's in the presence of peroxides. And for the simple ionic addition, we're going to do Markovnikov. That is, the halogen will bind to the carbon that gives the most stable carbocation. Peroxides, we will do anti-Markovnikov. Carbon, bromide will add to form the most stable radical, which means that the halogen is on the other carbon, the anti-Markovnikov carbon. Any questions? All right, next reaction. Instead of HBr or HCl or something, if we simply take an alkene and react it with a halogen, so this is bromine or chlorine or iodine, what's going to happen is we're going to form a 1,2 dihalide. So both of the halogen atoms are going to add 1 to each of the alkene carbons. Not only that, but there's stereochemistry here. In this addition, the halogen atoms always come in trans to each other. So we form a 1,2 dihalide trans stereochemistry. Now, understanding why we have trans stereochemistry is actually fairly simple. Mechanism of the reaction looks something like this. What we're going to do first is take our alkene pi cloud, lots of electrons, right? Lots of electrons. And that's going to attack bromine, Br2, or chlorine or iodine. We're going to split, in this case, the bromine-bromine bond, and one of these bromines, if the equivalent of Br+, is going to wind up sitting here on top of our alkene. This is a distinct intermediate, not just a pi intermediate. This is real. This is called the bromonium ion. Again, it's nothing more than a bromine sitting on top of the alkene pi system. It has a positive charge. Now, in order for this to give rise to product, Br- now has to attack, doesn't it? You could argue that Br- could attack from either the top or the bottom. However, the bromonium ion is huge. So here's our bromine sitting above our alkene pi system. And this is very, very large, isn't it? In order to give rise to products, we have to attack either this carbon or this carbon. And frankly, this is so big that you just can't get there. So the only way that Br- can attack is from the bottom. And when it does, it generates trans stereochemistry. So it has to come in the opposite face, simply because the bromonium ion is so big. Let's go ahead and look at a movie. It always seems much more real if you have a movie. Again, this is from McMurry, 6th edition. And here we took 2-butene, and we're going to simply add Br2. Mechanism, once again, going to attack, make the bromonium ion. Br minus is going to attack backside to give us trans stereochemistry. Step 1, bromine comes in, deposits the bromine there. This is our bromonium ion. Step 2, Br minus approaches from the opposite side, and we get our trans 1,2 dibromide. Br2 comes in, we form the bromonium ion intermediate. Br minus attacks from the opposite side, and we get our trans stereochemistry, our 1,2 dibromide. Remember, the reason that we have to have the backside attack is that the bromonium ion here is so big. Only real way we can get at this carbon is from the opposite face. Yeah?
Why do you say 1,2 dibromide?
I'm sorry.
Why do you say 1,2 dibromide?
1,2, well, 1,2 simply refers to the alkene carbons.
Oh, okay.
Not at all to the molecule and its numbering system. 1,2 dihalide simply means they're next to each other. All right, take these alkenes, add bromine. Look at this reaction now. We say, okay, it's an alkene. We're adding bromine. I know I'm going to make a 1,2 dibromide, okay, adjacent to each other. I also know the stereochemistry will be trans. So we're going to get one bromine here, one bromine here. Trans doesn't really have a meaning here because there's all single bonds, but we could draw it this way. Obviously, you could draw it any other way you want. Initially, you must form the trans product. It will then rotate any way it wants. Now next we have cyclohexene, don't we? Now we need to remember our stereochemistry. Initially, the bromines are going to be on opposite faces, aren't they? They're adjacent to each other. That means that initially, the product we're going to make is going to be a 1,2 dibromide, but the two bromines are going to be axial, so they must be opposite from each other. So here I've added, and I've made a 1,2 dibromide. Again, the bromines are both axial because they must come in on opposite sides. Now, as soon as we write this, we look at it and say, oh my goodness, that's not going to work, is it? So we want to draw this 1,2 diequatorial because this is much more stable. So we're simply going to do a ring flip here. Both of these axial bromines will now be equatorial. Initially, you must form diaxial, then it would quickly undergo ring inversion to to give diequatorial. And finally, our methylcyclopentene here. We have to somehow show stereochemistry with this one. Again, we need to be able to show that the two bromines are opposite each other, one above the ring plane, one below. Something like this would work. Any question? So we've done HBr, HBr peroxides, and now halogens. Let's take this one more step. If you take a halogen in water, you form hypohalite. If you take chlorine and put it in water, actually they use sodium hydroxide solution, you get bleach, sodium hypochlorite. Well, turns out that hypohalogens like HOBr, HOCl add to alkenes. When they add to alkenes, you form what's known as a halohydrin. In a halohydrin, we have a halogen on one carbon and a hydroxyl group on the adjacent carbon. So again, the addition is 1, 2. That is, they're adjacent to each other. It's actually a haloalcohol, in this case a bromo alcohol. Just like with the addition of bromine, the halogen and the hydroxyl group come in trans to each other. So it's just like the other. We'll see that the mechanism for this is exactly or very, very similar to what we saw for the other. What we're going to do is take HOBr, form a bromonium ion, and then instead of attacking with Br minus, we're going to attack with OH minus to give us our product. Let's look at a movie. Before that, I guess I'm supposed to say, there is regiochemistry here as well as stereochemistry. Stereochemistry is trans. The regiochemistry, if you look at your molecule, what you want to do is ask which of the carbons of the alkene is going to get the most stable carbocation. Okay? Whichever one gives the most stable carbocation, that's where the OH group goes. Okay? Let's look at our movie. Oh, I also supposed to say this. You can do this just with bromine in water. Like I said, chlorine in water, hypochlorite, bromine in water, hypobromite. In the lab, what you would really do is you would use this stuff. This is called N-bromosuccinimide. We'll actually use this in a lab. What this does is undergoes a cleavage here to give this succinimide anion and Br+. So Br+ is the stuff that's going to do our reacting. The conditions that you would see to describe this would be NBS, that's N-bromosuccinimide, in DMSO water solution. So that's just what you say. Or you could just write HOBr. All right. Step 1. This, well, I have 2 bromines here. I guess I shouldn't. But this is going to form a bromonium ion. Step 2, in the presence of water, water is going to attack. This ring is going to open. Our protonated alcohol is going to quickly lose a proton to give the halohydrin. Let's watch our movie. Step one, we're going to form a bromonium ion. Doesn't matter how we do it, all we need is Br+. Here's our bromonium ion. Step two, water is going to come in and attack on the opposite side. It's now positive, so we have to lose this proton. There it goes. And we have our transition. Once again, the regiochemistry is that the hydroxyl group is going to be on the carbon that would give the most stable carbocation. Now let's just talk a little bit about why that happens. This is our bromonium ion from propene, okay? We have a full positive charge here, but the way molecules work is that groups that are attached will release electrons to try to spread out this charge. Bottom line, when you have alkyl groups attached, it can spread out the charge better. Just like a tertiary carbocation is better than a secondary, better than a primary. So here we have a primary carbon, secondary carbon. There'll be more positive charge here. So this is the carbon that would give the most stable carbocation, and that's why the hydroxyl group attacks there. All right, so let's look at the problems. You see this and you say to yourself, okay, I'm going to add HOBr. I know I'm going to make a halohydrin. That's a bromine on one carbon, the hydroxyl group on the other. I know the hydroxyl group is going to add to the carbon that would give the most stable carbocation. So I look at my molecule. This would give a tertiary carbocation. This would give a secondary, wouldn't it? So where does hydroxyl go? On the tertiary. And the bromine goes on the secondary. This is our most stable carbocation. That is where the hydroxyl group will go. Product just looks like this. So this is how you work reactions. You learn to talk to yourself. Okay, you do. You learn to talk to yourself. You say, all right, alkene, HOCl. I'm going to make a halohydrin. I need to look at my alkene, figure out which carbon is going to give me the most stable carbocation. Here we have a tertiary, here we have a primary. This is our most stable carbocation. So what's going to happen? Hydroxyl group is going to be on the tertiary carbon, and the chlorine will be on the other. Then all you have to do is write the product. Hydroxyl group on the tertiary carbon, chlorine on the primary carbon.
OHS
You know
come
which
from
one.
I'm sorry?
OHS come from the top.
Well, remember these, we have a single bond, so we care about that. But remember the addition is going to be trans. Now that's going to be important here with our next one, isn't it? So with our next one, we're going to add HOBr. Hydroxyl group is going to go to the carbon that gives the most stable carbocation. And the addition will be trans. Here's our most stable carbocation, or the tertiary carbon. Draw the product. Make sure it looks like they are trans to each other. Hydroxyl group at the tertiary carbon, bromine at the secondary, and they must be trans. Yeah,
That second one, how do you know which one is factorial?
this is a 5-number ring, so it's not a
No, no, the second.
Oh, this one? Well, obviously it's going to undergo ring flip, so you could draw it either way. Probably this is a bigger group than the hydroxyl group. So this is probably the most stable isomer, but I wouldn't make you think about that. All right, so we've done HBr peroxide, we've done halogen, and HOBr. All of these guys feature an intermediate. Usually it's a positively charged species with a radical intermediate. It's a stable radical. Another example where we have an intermediate is the simple hydration. In hydration, what you're going to do is simply take a double bond and strong acid. You wind up with an alcohol. The regiochemistry is such that the hydroxyl group winds up on the carbon that would give the most stable carbocation. Therefore, this is Markovnikov addition. Now, this is a fairly brutal reaction, to be honest. We're going to have a carbocation intermediate. What happens is that the strong acid will protonate our pi system, just like we saw before. We will form this carbocation. Carbocation can undergo rearrangement. If it's not the most stable carbocation, we'll talk about that a little bit later. But once we have the carbocation, water will attack to give us the Markovnikov alcohol. When you look at this, you're supposed to say to yourself, just like HBr added, okay? You already know about HBr. Follows Markovnikov's rule, and instead of adding Br minus, we're simply adding hydroxide to the most stable carbocation. The requisite movie. Here we have an alkene. This is 2-methyl propene. This is going to be, first of all, be protonated. Going to pick up a proton to give the tertiary carbocation. Remember, we could have a primary or a tertiary. We will always add to give the most stable. That's going to be the tertiary. Water is then going to attack. Can come in from either side. We'll get the protonated alcohol. That will quickly lose a proton to give our product. So let's watch it. Step 1, we're going to protonate this thing. We're going to do it so that we form the tertiary carbocation. There's our carbocation. Next, water is going to attack. So would come from copper bottom. And we get the protonated intermediate here. This very rapidly loses a proton to give us our final product. Any questions? So, from your standpoint, when you see H plus H2O, think basically the same thing as HBr or HCl. Except, instead of adding the halogen, we're going to add the hydroxyl group to the carbon that gives us the most stable carbocation. And here's what they look like. Quickly jot down products for these reactions. Now, just like for the radical addition, on an exam, I said I would sometimes ask you to draw the most stable radical, right? On this one, I will quite often ask you to draw the most stable carbocation. So let's do it that way. Start off drawing our most stable carbocation, and then the final product. We could add to form a tertiary carbocation or a primary. We know that's a no-brainer. We will get the tertiary carbocation. Once you decide what carbocation you have, all you have to do is add hydroxyl group to that center, and our final product looks like this. This is called tert-butyl alcohol, or tert-butanol. We'll actually use this guy in lab also. Go ahead and do the next one. Draw the most stable carbocation, and then draw the final product. Our most stable carbocation. This is a tertiary center, that's a primary. We will make the tertiary carbocation. Once we have the tertiary carbocation, all we do is take the equivalent of OH minus, add it to that carbon, and we get the alcohol. All right, our last one here. This is a trick question. Here we have a methyl cyclopentene. Our methyl group is in carbon 3, isn't it? Now, both of our alkene carbons are secondary, aren't they? So when we protonate, we must form our secondary carbocation. However, this molecule also contains a tertiary center, doesn't it? Whenever you have something like this, where we form a secondary carbocation initially, and it's next to a tertiary center, we will get rearrangement. That means this molecule magically will go from a secondary carbocation to the tertiary carbocation. What happens is H minus at this point will simply transfer, called a hydride shift, from here to here. We'll have a movie of that in a while. When we do this hydride shift, we're left with a tertiary carbocation. So here's our initial secondary carbocation. This undergoes rearrangement, which means that the hydrogen with its pair of electrons simply slides from here down to here to give the tertiary carbocation. Now let's watch it slide again. Hydrogen with its electrons simply slides over to give us the most stable carbocation. Called a 1-2 hydride shift. Once we have the most stable carbocation, all we have to do is add hydroxide to that point, and we get our final product. Now, you know, rearrangements can be fun. They're usually not very useful. You usually wind up with real mixture of products. And hydration itself is just kind of an ugly reaction. Turns out that there's a better way to make a Markovnikov alcohol. When we say Markovnikov alcohol, all that says is hydroxyl group on the carbon that gives the most stable carbocation. Okay? There's a better way to do this, however, other than just acid and water. This is called Oxy of Curation. What you do instead of using strong acid is you use mercury 2 acetate. Mercury 2 acetate gives exactly the same product, except no rearrangement, and it's so much more civilized. Only downside is that you wind up with a reaction pot full of mercury, which you have to flush down the sink, and it goes to IOA anyway. But it's a two-step reaction. First thing we do is add our mercury 2 acetate. Then we have to take this stuff, sodium borohydride. We'll use this in lab too. This is a reducing agent. The reason we have to do this is that in the first step, we wind up with a mercury attached at this point. So we have to get rid of the mercury with borohydride. The way this works is something like this. Step 1, remember our bromonium ion? I hope you do. Bromonium ion, we said, just kind of sat there on the alkene pi system, didn't it? And it was positive, right? Well, this forms a mercurinium ion. It looks, for all the world, like a bromonium ion, doesn't it? It's just sitting there on the alkene pi system with this positive charge. And what happens? Hydroxide is going to attack backside, because mercury is even bigger than bromine. Going to attack backside, break our bond, and we wind up with this intermediate. Now, if you just let it sit here like this, if you didn't do our second step, you would have this organomercurial. They're fairly toxic. You don't want to play with them. You don't. But, so we need to get rid of our mercury. That's why we do our second step. Sodium borohydride replaces this with a hydrogen. Poof, it's gone. and we have our Markovnikov alcohol. Much, much more civilized reaction. Yeah.
What do you mean by that? Faster? Do you mean just faster?
No, you don't get rearrangement. If you do, and I believe that we actually do an elimination reaction with a strong acid, I'm not sure. But whenever you're doing a strong acid reaction with an alkene, you get this flask that's full of this black tarry junk. So it's just a really messy, ugly reaction. Lots and lots of side products. Not something you want to do for real. This, nice and clean, and you get your product. Don't have to worry about rearrangement. Let's just look at an example where this is useful. Let's say that your entire grade in organic chemistry depended upon making this molecule. And you had to do it using hydration of an alkene. Right? Well, you would look at this and say, okay, I have my hydroxyl group bonded to a tertiary carbon, don't I? Now, normally that would be good, except in this molecule, we have a benzylic carbon, don't we? The benzylic carbocation would be more stable than the tertiary. So if we simply took an alkene and tried to do hydration, we would rearrange and the hydroxyl group would be here. If we started off with this alkene and we dumped in acid and water, we would initially form a carbocation out here, but it would rearrange, just like we saw, until it was at the benzyl position. It would be a messy reaction, and you would not get the desired product. So what you have to do here is do this, instead of using acid and water, do this with mercury 2 acetate. That means we will get Markovnikov regiochemistry here, that's that carbon, but we won't have rearrangement. Therefore, step 1, we simply dump in mercury 2 acetate. That would give us the mercury bonded here. Step 2, for a hydride, get rid of the mercury, have our product, no rearrangement, and we all pass organic chemistry.
Let's do it.
Got it. All right. Markovnikov regiochemistry, no rearrangement. All right, that's our first set. Our second set of reactions are going to look like this. These are largely going to be different mechanisms. What we did in the first one were ionic mechanisms, where we have an ionic or a radical intermediate. Here we don't. We're going to have different types of intermediates, but not ionic and not radical. This is called hydroboration oxidation. This gives us anti-Markovnikov regiochemistry. And instead of trans, this goes syn or cis. Here we have reduction. Take a double bond, make an alkane out of it. This is syn or cis addition. Osmium tetroxide or permanganate, 1,2-diol. Again, cis or syn addition. And then finally, really neat things here. We're going to make cyclopropanes. This is a dichlorocyclopropane. This is just a cyclopropane. Nice simple reaction. chloroform and base, or diethylmethane, zinc copper amalgamate ether. So let's get started. Hydroboration oxidation. If we looked at this alkene here, and we did either hydration or reaction with mercury 2 acetate, we would get Markovnikov regiochemistry, right? That means the hydroxyl group would bind here. What if we wanted the hydroxyl group here? This is when you do hydroboration oxidation. What we're going to do is add a hydroxyl group and a hydrogen. These are going to come in on the same side of the alkene. This gives us a cis or syn addition. It's a two-step reaction. Going to use BH3 in an ether. This is tetrahydrofuran, THF. Step 2, we're going to dump in peroxide. Initially, we make an organoborane and then convert it to the alcohol without peroxide. So let's see how this works. Step 1, our borane simply approaches our pi system. And when it does, we're going to transfer the moral equivalent of H minus, one carbon, and boron to the adjacent carbon. This is a concerted reaction. That means that both of these things happen at the same time. Okay? Not stepwise, concerted. Why the regiochemistry? Well, there's two reasons, really. First of all, this alkene, because this is a tertiary center, this carbon is going to have a slightly greater positive charge than the secondary one. So that's one. The second one is just simply steric. When you do this, you actually don't just have BH3. There's lots of stuff attached here to our boron. And it's big. So it's going to avoid the methyl group and head for the least hindered carbon. All right, so we're there. In one magic step, H minus goes up, boron goes here, and we get the organic borane. Now, our second step, we have to get rid of the boron. We're going to get rid of the boron by dumping in peroxide. Peroxide, you don't need to know the mechanism. It's in the book if you like to look. Peroxide will add to the boron. Again, you get a concerted rearrangement. The oxygen swaps with the boron, and we wind up with the alcohol. This is syn or cis addition because these things happen on the same side of the alkene pi system. They slip, one goes one way, one goes the other at the same time. Now there is one important thing to remember here. The second step in this reaction is peroxide and base. Now, if you were to take this and forget our second step and simply dump this into water, what would happen is, instead of the alcohol here, like you should, with water, we simply get the hydrocarbon. So, remember, make sure second step is always peroxide. Of course I made a movie. Here we're going to simply take ethene But again, our mechanism. This is going to add, again, from the same side of our double bond. We will get the organic borane. Second step, peroxide, boron goes, and we're left with the hydroxyl group. Let's watch the movie. Step one. Here comes our boron. And you'll note, this is what I mean by concerted. They both fly at the same time. This is our transition state. And you see they both go on the same side. Our second step, to add peroxide, doesn't change the orientation. So we wind up with syn or cis stereochemistry. Let's see if we can make this work again. Watch it as it comes in. Both bonds happen at the same time. There's the transition state. And there's the organic borane. Oxidize it, and this goes to the alcohol. Any questions? All right, let's do a couple quick problems then. Take these alkenes, do hydroboration, oxidation. Remember I said you talk to yourself. What do you say? You say, well, this reaction, I'm going to get an alcohol. My regiochemistry is going to be anti-Markovnikov. And the hydrogen and the hydroxyl group are going to be cis to each other, or syn. We look at our first one here. We have a tertiary carbon, we have a secondary carbon. Where does the hydroxyl go? Anti-Markovnikov, so hydroxyl group is on the secondary carbon. Hydrogen goes to the tertiary carbon, and the two must be on the same side. So draw your bicyclic structure. Because we have one carbon bridge up top and a two carbon bridge on the bottom, addition is going to be from the top here, because this is smaller than this. And the product is going to look like this. Hydroxyl group on the secondary carbon, hydrogen on the tertiary carbon, and they're on the same side. Go ahead, say your magic words, draw your product. Anti-Markovnikov, hydroxyl group adjacent to the most stable carbocation. That's tertiary, that's secondary. Hydroxyl goes to secondary. Any questions? Well, let's continue with the notion of cis or syn addition. And let's look at catalytic hydrogenation. Here we're going to take an alkene and make an alkane. We're simply going to add hydrogen to it. When we do this, one hydrogen goes to each carbon. Just like we just saw with our hydroboration, the addition is going to be cis or syn to each other. Now this reaction occurs with hydrogen gas and a metal of some sort. Typically you need a catalytic metal, so platinum, palladium, rhodium, those guys work. The way this reaction works is it's something that happens on the metal surface. Okay, it's on the metal surface. So step one, we have our chunk of platinum. And we have hydrogen. The hydrogen will come down to the surface of the platinum and it sticks. Basically, the hydrogen H2 splits into two hydrogen atoms, stuck to the surface. Now, step two, our alkene comes in. It also comes and sits down on the surface. It has this big pi cloud, remember? Lots of electrons, comes and sits right there on the metal surface. Now, we have hydrogen and the alkene sitting there on the surface next to each other. They say hello, and our two hydrogens simply slide over to the alkene, and we wind up with the alkane. Because both hydrogens add at the same time from the same face, this is cis stereochemistry. So what do you have to remember for this? You simply say, okay, start with an alkene, we're going to make an alkane. If there's stereochemistry involved, the hydrogens will be cis. That's what you say to yourself. So let's practice saying it. Both hydrogens are going to add. They're going to add on the same side, but it doesn't matter because it's a single bond, isn't it? All we have to do is convert the alkene into the alkane. With our next one, same thing. The alkene's going to go to alkane, but we do have a ring. So we have to worry about stereochemistry, don't we? We must show that the hydrogens both are on the same side. Once again, they're probably going to come in through the top, because there's only one carbon, two on the other side, and that would be our major product. Go ahead and draw our 1,2-dimethylcyclopentene reduction product. All we have to do is show both hydrogens on the same side of the ring. Does this molecule contain chiral centers? Absolutely, two of them, right? Is it a chiral molecule? Oh, nope, it's meso. Plane of symmetry right down the middle. Any questions on hydrogenation? Very, very simple reaction. Well, as long as we're doing cis addition, let's do formation of 1,2-diols. You can do this two ways. You can use permanganate. Permanganate is purple, it's dirt cheap. Really. It's cheap. It's simple. They use it in water purification to remove organics from Lake Michigan before you drink it, etc. This is osmium tetroxide. It's extremely expensive and extremely poisonous. Nonetheless, if you have spent the last 4 years isolating an alkene that you need to convert to a 1,2-diol, you would use osmium tetroxide because it works. It works really well. Permanganate doesn't work as well, but it's dirt cheap. This is what most people would use, unless it was a very rare, expensive molecule. In both of these reactions, we get 1,2-diols, and in both of them, they are cis. Focus here on permanganate. It's the most common. The reason that this is cis addition is that both oxygens come from the manganate anion. So MnO4- simply adds to the alkene pi system from one side or the other. This is an unstable intermediate. It breaks down, we get MnO2, and we're left with a 1,2-diol. Again, cis stereochemistry. Very simple reaction, either permanganate or osmium tetroxide, cis 1,2-diol. Let's do a couple. We look here, we see we have an alkene. We have osmium tetroxide followed by sodium bisulfite. You need the bisulfite whenever you use osmium because the osmium intermediate doesn't break down spontaneously. So you need to push it off, but okay. Final product is going to be simple. Both oxygens are going to come from the osmium. They're going to be on the same side. You could draw this in a chair conformation, or you could show the stereochemistry with wedges. Unless I ask for one or the other, something like this would work fine. All you have to do is demonstrate that both hydroxyl groups are on the same side. Go ahead and draw the product for the permanganate oxidation of 1-methylcyclopentene. Once again, all you have to do is show stereochemistry. You could do this with a very nice perspective drawing, or you could again just simply use wedge bonds. Let's continue our concerted reaction mechanisms here with our cyclopropanation. Here we're going to take an alkene and we're going to make a cyclopropane ring. Now this sounds kind of magic, but it's really very simple. It involves a carbene intermediate. If we take chloroform and strong base, we can form what is known as dichlorocarbene. We'll see that in a second. Dichlorocarbene will then simply sit on the alkene pi system, just like bromine did, just like mercury did, and form this cyclopropane structure. This is a 1,1-dichlorocyclopropane. If we don't want the chlorines, we can use this stuff. This is diiodomethane, and we do it in the presence of zinc and copper. This generates CH2, that's carbene itself, but once again, that just sits on our double bond, and we get the cyclopropane. Another way that you can do it in lab, this is a separate thing, is to use what's called diazomethane. A diazomethane, if you look at this is nitrogen, isn't it? N2, kind of stuck to a CH2. This is going to split off. Nitrogen is going to take its electrons and go away, and it's going to leave CH2. That's carbene, and that'll simply add. How does this work? Well, sorry. I was supposed to say this. This is the chunk that comes from dichlorocarbene, and this here is the chunk that comes from the carbene. All right, talk a little bit about carbenes. What happens is we do an elimination of HCl from chloroform. And that leaves us with a carbon with a pair of electrons bonded to two chlorines. This is what it looks like. It's sp squared, and it's not charged. It's a carbon with really only two things bonded, and it's not charged. It's a carbene. It's extremely reactive. Carbon likes 4 bonds, doesn't it? This thing is going to add, going to sit on the pi system quickly and make our compound. Let's look at our movie. Step 1, we're going to remove HCl to get dichlorocarbene. Dichlorocarbene is going to sit on the alkene, and poof, in a concerted reaction, you have your stuff. Here we go. This is chloroform. Step 1, we make carbene. Our base comes in. Now we have carbon, 2 chlorines, and a pair of electrons. Very reactive stuff. This sits on our pi system. Boom, we make 2 bonds, and we have our product. Step 1, we make carbene, dichlorocarbene. Step 2, this sits on our alkene pi system. Both bonds are made at the same time, and we get our product. Let's just do a couple quick ones. We look at our reaction conditions. We see diiodomethane in zinc copper amalgam. We say right away we're adding carbene. All I have to do is convert my double bond into a cyclopropane. That's all I have to do. Redraw this thing with a 3-membered ring. Looks funny, but that's it. take your double bond, convert it to a cyclopropane. Do the same thing now for chloroform. Just remember you're going to make the dichloro cyclopropane. This is going to become our cyclopropane. Remember, 2 chlorines come along for the ride. All right, believe it or not, we're almost done. We just have to deal with simple oxidation reactions. If we take an alkene in the presence of a peroxide, we're going to make a cyclic ether called an epoxide. We all know epoxy resins. This is the epoxide. The next 3 reactions here split the carbon-carbon double bond. So what we're going to do is actually split this thing open. If we have, well, depending on what's attached here, with ozone, followed by, this is called dissolving metal reduction. We'll talk about that. We will split our carbon-carbon double bond. Each carbon becomes a carbonyl, and we make aldehydes and ketones. Instead of doing dissolving metal reduction, we could do oxidation. So for our second step, if we dump in an oxidizing agent like peroxide, we still split, both carbons still become carbonyls, but instead of aldehydes, we get carboxylic acids and ketones. And finally, an example of a brutal reaction. If we take permanganate in the presence of acid, we split our carbon-carbon double bond. Depending on what's attached, we can get carboxylic acids, CO2, or ketones. All right, let's look at these. First guy, epoxides. This is an organic peracid. Okay, peracid. We saw peroxides. The peracid, we have a carboxylic acid down here on one side. Peracid, you just have too many oxygens. Okay? Remember how carbene kind of came in and just sat there on the pi system and magically inserted itself, right? We saw that. Well, a peracid does the same thing in one magical step. What it's going to do is donate this oxygen to the pi system. Kind of looks like this. Oxygen goes over, this comes out as the carboxylic acid, and again, magically, we have the epoxide and just left over carboxylic acid. Don't have to worry about the mechanism, it's magic. But again, the oxygen is just inserted into the alkene pi system. All right, well, this is a very simple reaction, isn't it? Let's go ahead and look and see what this would look like on an exam. Peracid, you know that because there are too many oxygens. Go ahead and draw your products for your 3 oxidation reactions. Now the operation here is really, really simple, isn't it? It's concerted, there's no rearrangement. All you have to do is take your double bond and make an epoxide out of it. Here, these are our two double bond carbons, our alkene carbons. We simply put the oxygen in between them. Here we have 1-ethyl cyclohexene. All you need to remember is the carbons of our double bond are going to be an epoxide. And finally, here is 2-methyl propene. Again, we're just going to convert our two alkene carbons into an epoxide. How simple is that? Now, epoxides are neat. Again, like I said, you use these in epoxy resins. We don't talk about polymerization in this course. We'll do it in the next course. But when you do an epoxy polymerization, you're going to basically open the three-membered ring and link things together. But there is one really neat use for an epoxide. Remember, we talked about how to make 1,2-diols with permanganate, right? What do we know about that? We know it's concerted. We know we have a manganate intermediate, and the addition is cis. Well, if we have an epoxide, and we take that and dump it into aqueous acid, well, step one, we're going to protonate the oxygen, of course. Now remember what happened to our bromonium ion? Something came and attacked from the backside, didn't it? Well, here, water does the same thing. And so just like the addition of bromine, or HOBr, gave trans product, this gives a trans 1,2-diol. So now you can choose if you want your 1,2-diol to be cis or trans. Here we have cyclohexene. And look at this, per acid. We know that this is going to give us an epoxide, right? But we have a second step, aqueous acid. That's going to open the epoxide and give us a trans 1,2-diol. Now I've drawn these both equatorial. Again, initially they would both be axial, but they would ring invert to give the diequatorial. Or we could do this with permanganate. If we did this with permanganate, what would happen? We will get a 1,2-diol where the oxygens are cis. Now in a 6-membered ring, 1,2 cis means axial equatorial. So that's one of the reasons epoxides are neat. We can do the two-step reaction where we make the epoxide and then hydrolyze it to give trans 1,2-diol. If If we wanted the cis instead, we would just use permanganate, get a cis 1,2-diol. Now, you might have guessed this is a standard exam question, isn't it? I'm going to give you a structure and say, how do I make that? And you're going to say, well, let's see, these are trans. So I want to do per acid followed by acid. Or if I gave you cis, you would do permanganate. Any questions? All right, we're getting closer. Let's start splitting our double bonds. Everyone knows about ozone, right? When you have a nice summer thunderstorm coming, lightning generates ozone. We'll see in chapter 10, ozone can be a very, very good thing. It can also be very toxic. But ozone reacts with alkenes to form an unstable, very unstable intermediate called an ozonide. Now, what have we done with so many things with our pi system? We just take and sit it down on top of the pi system, don't we? That's how you make the ozonide. O3 comes, sits, boom, all three oxygens attached to our carbons. Once we have the ozonide, we can break this open, and in the process of breaking it open, we're going to break the carbon-carbon bond that was in our alkene. Okay? So the conditions we use here, just zinc and acid, is called dissolving metal reduction. We split our double bond here. Each of these carbons gets a carbonyl. So this is a carbonyl, that's this guy. There's hydrogen attached, so it's an aldehyde. This carbon has two hydrogens attached, so it's formaldehyde. All we've done is split the carbon-carbon double bond. Each one becomes a carbonyl with whatever else is attached to it. Let's see how this looks. Oh, let me talk about dissolving metal reduction because we'll see this several times. Dissolving metal reduction. This is zinc actively dissolving in acid. So if you take a little chunk of zinc metal and you have hydrochloric acid or something in your flask, all you do is add little chunks. And what's it do? It fizzes. So this is fizzing metal in acid. When it does this, it generates hydrogen radicals. Hydrogen radicals are what actually open up the epoxide. But you don't have to know that yet. All right, quickly split our double bonds here and predict our products. Each of the alkene carbons will become a carbonyl. Everything that is attached stays attached. All right, we're going to split the carbon-carbon bond here. This carbon, we have two hydrogens, it will be formaldehyde. This one, we have one hydrogen, it will be acetaldehyde. Also called ethanol more properly, and this is methanol. Here we're splitting our carbon-carbon double bond. We have a hydrogen attached to this alkene carbon, so that will be an aldehyde. We have two methyls, so this will be a ketone. The ketone will be acetone, that's 2-propanone. This will be a 1, 2, 3, so it's a propanal. Everything that is attached stays attached. Now these are always fun. We're going to split our double bond. We're going to be left with one molecule, but each of these is going to be a carbonyl, isn't it? So here we're going to have a ketone from this guy with an ethyl group, CH2, this is a carbonyl. Then we're going to have 1, 2, 3, 4 CH2s. And this is going to be a carbonyl, hydrogen here, so it's an aldehyde. Splitting it right here, it looks like that. Both alkene carbons become carbonyls. This guy is a ketone. This one is an aldehyde. Now I've kept it wrapped up here so you could see that, but obviously, you can write this out long chain. Go ahead and do the same thing here with cyclopentene. Both of these are going to be aldehydes. Here we're going to have an aldehyde, then 1, 2, 3 CH2s, and then our next aldehyde. Open chain, it would look like this. Aldehyde, 1, 2, 3 CH2s, and then our next aldehyde. Now the neat thing about ozonolysis is that you can make aldehydes. Aldehydes are useful molecules when you do synthesis, but they're difficult to make because they're easily oxidized. They're easily converted to carboxylic acids, very easily. So instead of using very mild ozonolysis with reduction, if you use something stronger, like acidic permanganate, we're going to do the same basic reaction. We're going to split our bond, but any time that you would make an aldehyde, it will be converted to a carboxylic acid. So think about the same logic here. Split your double bond and say, okay, if this was ozonolysis, what would I get? I would get an aldehyde, and I would get an aldehyde. But it's permanganate. That's a strong oxidant. Permanganate takes the aldehyde, makes a carboxylic acid, and actually it takes formaldehyde all the way to CO2. Here we have alkyl groups everywhere. If we split this, we simply make ketones. So we wind up with ketones, carboxylic acids, and CO2, depending on what's attached. So let's look at two examples here. If we take this exocyclic alkene, ozonolysis followed by reductive workup, what will we get? Step one, you say to yourself, I'm going to split the carbon-carbon double bond. Split it. Boom. It's ozonolysis. Everything that was attached stays attached. Like Las Vegas, I guess. sort of. That means our top carbon is going to split here. Our top carbon is going to have 2 hydrogens. It's going to be a carbonyl. That is formaldehyde. Our bottom carbon has 2 alkyl groups. It's going to be a ketone. Now in our next one, we have a methyl cyclopentene. We see we have permanganate acid. Again, we know we're going to split our carbon-carbon double bond. Boom. Okay? So we split it. The top carbon will become a carbonyl. It has a methyl and a CH2 attached. So it's a ketone, isn't it? It stays a ketone. Our bottom carbon has a hydrogen. If this was ozonolysis, it would be an aldehyde, but it's manganate. So it's going to go to a carboxylic acid. Our ketone and our carboxylic acid are going to be separated by 1, 2, 3 CH2 groups. If you haven't written it, do it. Ketone, 3 CH2s, carboxylic acid. Ketone, 3 CH2s, carboxylic acid. And that is our last chapter 8 reaction. Now, let's just all relish in what we know. Draw the products for each of these simple reactions. Remember, it's okay to talk to yourself quietly. Our first reaction, we're adding HCl, that's halogen acid. What do we know about it? Going to do a carbocation intermediate. It's going to be Markovnikov regiochemistry. And the chlorine is going to add to the carbon. It gives the most stable carbocation. Well, here they're both the same. So it doesn't matter where you put it. This is simply going to be chlorocyclopentane. Our next one, we look and we see HBr peroxides. Okay, what did we say? I'm going to make an alkyl bromide, and it's going to be anti-Markovnikov. That means we're going to form the most stable radical, and then bromine's going to be on the other carbon. The most stable radical would be here at the secondary carbon, which means that bromine must be bonded to the primary. Anti-Markovnikov alkyl bromide. This was our most stable radical at the secondary carbon. Bromine adds to the primary. Addition of halogen, what do we know about that? We're going to form a 1,2 dihalide, and they're going to be trans. So somehow we have to draw this thing so that it is clear that the bromines are on opposite sides. You could draw a 6-membered ring in a chair, that'll work, or you could use wedgies. If we drew it in a 6-membered chair, again, I put the 2 bromines here, both equatorial. We know that initially they must both be axial, but this would be the most stable conformer. Or you could simply do wedges with one coming toward you and a dashed one going away. Next, we did the addition of, well, again, we're doing addition of HCl. Not next. Same as our first reaction. Again, we know this is Markovnikov addition. Chlorine is going to bond to the carbon that gives us the most stable carbocation. We have a tertiary and a secondary. Where does the chlorine go? To the tertiary, of course. We moved on after the addition of bromine to the addition of HOBr. What do we remember? Intermediate bromonium ions. Hydroxide would add to the carbon that gives the most stable carbocation, but here they're equivalent. The addition is trans, however. So we must draw our product so clearly bromine and the OH are trans. That would do it. Or you could use wedges. Simple hydration. Ugly reaction gives lots of rearrangements. This is simple enough that it would work. We're going to form the Markovnikov alcohol. That means OH is going to be bonded to the carbon that gives the most stable carbocation. We have a secondary and a primary. That means the OH is bonded to which carbon? The secondary, of course. More civilized way to do hydration, mercury 2 acetate followed by borohydride reduction. Once again, this is going to be Markovnikov. That means the hydroxyl group is bonded to the carbon of the alkene that would give the most stable carbocation. We have a tertiary and a secondary. Where does it go? Tertiary, of course. Now let's revisit hypohalite reactions. Remember we said up there in our first one that we're going to get Markovnikov regiochemistry relative to the hydroxyl group. So the OH is bonded to the carbon that gives the most stable carbocation. Up here it made no difference. Down here it does. Tertiary carbon, secondary carbon. This is the Markovnikov carbon. This one gets the bromine. That's our halohydrin. All right, if you look at your handout, this goes on for like 8 or 10 more slides. We're not going to do those. not today. On Thursday, we're going to do the Finkelstein reaction. In the Finkelstein reaction, there's a handout, please read it, it's kind of neat. Finkelstein reaction is an SN2 reaction. We're going to talk about those, I think, chapter 11. But in the Finkelstein reaction, you use acetone, sodium iodide, etc. As part of the procedure, though, you set up a reflux apparatus. Reflux apparatus, you have your round bottom flask, have your condenser, except the condenser is vertical. You're not distilling, it's simply vertical. It's designed so that you heat it up, the vapors go up, condense, dribble back into the flask. Reflux. For the Finkelstein, you need to set it up and reflux for 45 minutes. So here's the plan. Everybody will get their Finkelstein running. We will then adjourn to this end of the room, and we will go through the last 8 slides here. So please, take these, work all these problems. This is what an exam kind of looks like. Work all these reactions. And then we'll check them during our 30 to 40 minute reflux next Thursday. Sound like a plan?
Yes.
Sounds good to me. All right.
You
Again,
here?